Hi everybody, welcome back. This is Chapter 4, Lesson 8 for AP Chemistry, and we're going to talk a little bit about titrations today and do a couple more practice problems with those, as well as assigning oxidation state. So it's a little bit of both today. You performed a titration today, so just to review, the stuff in the syringe that you're adding to your solution is known as your titrant. That's what you're titrating with. That's what you're adding to your solution that was in your flask. In our case today, it was sodium hydroxide, right? We were adding the sodium hydroxide to our KHP. The thing that we're analyzing is called our analate. So our KHP was our analate. And the idea is, in a titration, that you want to add exactly enough base to react with all of the acid that's present. Not more and not less, exactly enough. So that at the end point, which we know is the equivalence point of the titration, there is no excess hydrogen ion, there is no excess hydroxide ion, all that you've truly made is water. So we make an assumption that the moles that we have present, or the moles of our acid, are equivalent to the moles of our base at the equivalence point in a titration, or the end point. Which is why when you do your calculations tonight, you have your moles of KHP that you added, that you can get because you know the grams, about 0.3-ish, right? You can get the grams, and that will give you the moles. And the moles of base that you add to reach the end of the titration, we assume that those are equal. When in reality, obviously, most of you over-titrated. And I know it was just a drop, so it shouldn't make any real difference in our calculations, but that's the idea. So whatever the moles of KHP were that you added, those are the moles of NaOH that it took to get to equivalence. So then you'll have the moles of NaOH and the volume of NaOH, and you can find the molarity. So really we do it to find or confirm an unknown molarity, okay? So we did the first two practice problems. Let's try another one. An environmental chemist analyzed the effluent from an industrial process known to produce compounds carbon tetrachloride and benzoic acid, a weak acid that contains one acidic hydrogen per molecule. So even though this benzoic acid up here has 6 hydrogens, only the front one ionizes and is acidic. A sample of this effluent, so we've got something that comes out of an industrial process. It really contains two things. It contains carbon tetrachloride and it contains this benzoic acid. And we have a sample of this effluent and it weighed 0.3518 grams. So this whole thing weighed 0.3518 grams. They dissolved it in water, and then they titrated it with some NaOH. So they took this and they reacted it with NaOH for neutralization, which certainly applies that the NaOH reacts with the acid, right, in this effluent. It took 10.59 mils of 0.1546 molar NaOH. Calculate the mass percent. So they want the percent by mass of the HC7H5O2. And again, to calculate mass percent, it's the mass part over the mass whole times 100. We know the mass whole here. The mass of the whole effluent is 0.3518 grams. So what our goal in this whole problem is to do is to find the mass of acid inside that effluent. How much of that is due to the acid, really, right? So what you need to recognize is that what reaction is going to happen when you add the NaOH to this mixture? Well, this is a base. And so when you add a base to a mixture, it will react with the acid. It's not going to react with the CCl4. So our reaction of interest then, again, always step one, write the reaction, is the HC7H5O2 reacting with the NaOH. They undergo double replacement to make NaC7 H5O2, and water. Okay? Now, what we know is the molarity and volume of this, 10.59 mils of 0.1546 molar. So we know the molarity and volume that it took to neutralize that acid. We can get the moles. The moles equal the molarity times the volume in liters. So our molarity is 0.1546 times our volume in liters, which is 0.01059. And that will give me my moles of base that it took to reach equivalence, which is 0.001637. It looks like we're in 4 sig figs, so that's good. Moles of NaOH. Now, just like any other problem that we've done, if you know the moles of one thing in the reaction, you can find the moles of anybody else, because 0.001637 moles, according to the equation, for every 1 mole of NaOH that reacts, you will also react 1 mole of the acid. So that will give us our moles of acid, which will be the same, and then we can convert it to grams by multiplying by the formula mass, so that we can get the grams of acid that were present originally in the sample. So let me just pause and calculate the formula mass, and then we'll come right back. Okay, I had the formula mass to be 122.13 grams. So then you multiply that by 0.001637, and you should come up with 0.1999 grams of the acid, which, remember, is what we needed, if we can just go back up here, to calculate the percent by mass. So I'll rewrite it down here so it's a little easier to follow. The percent then of your HC7H5O2 is the mass of that in your sample, 0.1999 grams, divided by the mass of your whole effluent, which was 0.3518 grams, times 100. And again, I leave all my numbers in the calculator, so let's look at, I think every number that was given to us is in 4 sig figs there. So we'll go 4 sig figs, and you should have 56.83% is your final answer. Let's try another one. A student carries out an experiment, kind of like you, to standardize a sodium hydroxide solution. To do this, the student weighs out 1.3009 grams of KHP. KHP has 1 acidic hydrogen. They dissolve the KHP in distilled water, just like you did. Added phenolphthalein as an indicator, just like you did. And titrated the solution with sodium hydroxide to the end point. The difference between the initial and final burette readings indicates that 41.2 mils of NaOH is required to react exactly with the 1.3009 grams of KHP. Calculate the concentration of sodium hydroxide. So this is exactly what you did in your lab, except they used a lot more because we did the microscale titration. So we have the KHP, which again, I told you it's this crazy acid. I just like to abbreviate it HA. That's our KHP. We're going to react that with the NaOH. They perform proton transfer or double replacement. NaA plus H2O. Okay? And we are starting with 1.3009 grams of this, and it takes 41.20 milliliters of this. They want concentration or the molarity of your base. So again, this should be very much review for you for what you did in the lab. If you have the grams of KHP, just like you do, you can find the moles. According to the formula, 1 mole of KHP, isn't it nice when they give you the molar mass? 1 mole of KHP weighs 204.22 grams. So that'll give us the moles of KHP. Since I have the moles and I have the equation, I can find my moles of NaOH. According to the equation, for every 1 mole of KHP I react, I will need 1 mole of NaOH. So that will give me my moles of NaOH. So I take 1.3009, I divide it by 204.22, and I get 0.0637001 moles of NaOH. Now, I have the moles of NaOH and I have the volume of NaOH, so I can find the molarity of NaOH because it is the moles divided by the volume in liters. If you paid any attention, they did in the lab tell you to just divide by the volume in milliliters and then multiply by 1,000. That's okay to do too. I just think it's easier to convert it to liters first. So we'll take our moles and we'll divide it by our volume, 0.04120, and you should get the molarity to be 0.1546 molar NaOH. Okay? There you go. All right, let's skip forward a little bit. Our next section deals with redox reactions and balancing them. So just to remind you from Regents Chemistry that when we talk about redox, it's really the combination of 2 reactions. It's the combination of oxidation and reduction. And while acid-base reactions involve proton transfer, redox reactions involve electron transfer. LEO, loss of electrons, is oxidation, and if you lose negatives, your charge goes up, and your secret spy name is the reducing agent, because you make someone else gain. GR, if you gain electrons, GR, you're gaining negatives, your charge goes down, you are reduced, and your secret spy name is the oxidizing agent. In order to tell who is being oxidized or reduced, you need to know the rules to assign oxidation states. Okay? Here are the rules. You probably want to write them down. And you know what? I'll rewrite the rules. And you can write these on a separate sheet of paper or in your notes if you have room. So these are the rules for assigning oxidation numbers. Charges is the word you can use when you don't have enough room to write oxidation numbers. So any element by itself has a charge of 0. Unless otherwise written. You should assign charges in this order. Number 2, any group 1 compound, any group 1 element in a compound. Have a charge of +1. Number 3, any group 3 element, any group 2 element in a compound has a charge of +2. Okay, so group 2 in compounds are always +2. Fluorine is always -1 in compounds. Hydrogen is mostly +1 in compounds. The only time it's not is when it's in what's called a binary metal hydride, like group 1 with H or group 2 with H. And that makes sense. Since group 1 is +1, group 2 is +2, H will have to be -1. And finally, Oxygen's usually -2 unless it's with F or it's in a peroxide, because if it's F, it has to be positive. In a peroxide, it's -1.